Good morning. I'd like to look at today's lesson involving taking us from our understanding of the 68, 95, 99, 7 rule into a table of standard normal distributions. So first of all, let's review the 68, 95, 99, 7 rule. And so here's an example. It says, suppose the weight of navel oranges is normally distributed with mean 8 ounces, standard deviation 1.5 ounces. Now, this really would be written as mu equals 8 and sigma equaling 1.5, which means the truth is 8 and 1.5. So if I draw me a distribution, the center of this guy is 8, and this is 1.5 ounces. And so now the question is, what's the probability that a randomly selected navel orange is less than 5 ounces? So what I've written right here is essentially a translation of that English sentence into a mathematical one. And as it turns out, it doesn't matter if this has an equal to sign under it or not. So I usually more efficiently don't write it. Well, if I count out 1.5 standard deviations, this is going to be 6.5 and 9.5. And then again, I end up with 5 and 11. Now the question is, what's the probability I get something less than 5? And so according to my rule, in here, inside of 2 standard deviations is 95% of the data, which means that out here I have 5% of my data. I haven't drawn this perfectly. This kind of extends on, of course. And so down here on this region is going to be half of that 5%, or 2.5%. So let's look at another one. Same question stem for all of these problems, but now we have an orange that weighs more than 11 ounces. So I'm going to make my graph a little more efficient and show you how to standardize this. So I've got a mean of 8 and a standard deviation of 1.5. Now this 11 goes up here, and I'm trying to find the distance above it. Now you can probably tell that this distance right here is 3, which is 2 standard deviations. But let me remind you of how this standardization would work. So my z is going to be, I'll write it in generic form first, x minus mu over sigma. Or in other words, 11 minus 8 over 1.5. Telling me that 11 is 2 standard deviations above the mean, or if I change this to a 0, this is actually 2 standard deviations above the mean. And so now I've gone 2 standard deviations above the mean, and just like we had before, that means that this probability that I get something bigger than 11, or formally written 11 minus 8 over 1.5, z is greater than 2, that's going to be the 2.5%, because it's symmetric to what I had on this problem here. And so let's use this idea of standardizing it as we continue with part C. And part C says we want to find the proportion of oranges between 5 and 9.5 ounces. So this is 8. This is 1.5. We've gone down here from 5 up to 9.5. And this is cleverly done, of course, so that I've got 2 standard deviations over here and only 1 standard deviation in the upper direction. But we're showing the steps. So I'm looking for the probability that x is between 5 and 9.5. And so what I want to do is standardize those numbers, and we'll get the integers we expect, but it's 5 minus 8 over 1.5 is less than, now this x becomes a z because it's a standard score. And this is 9.5 minus 8 over 1.5. And so, as we see, this is 2 standard deviations below the mean, hence the negative. And this is 1 standard deviation above the mean, and therefore it's positive. And if I think about this a little bit, I know that this distance is half of 95, right? Because if it was all of 95, it would include both sides, right? If I went 2 standard deviations here and again here, I would end up with 95%. I only want half of that. And likewise, this region is half of the 68%. And so 95 divided by 2 plus 68 divided by 2 is, this is 47 and a half. This is 34. And so I can add those two guys together and get 81.5%. And so again, this means 81.5% of oranges will be between those two intervals. And while we've used the 68, 95, 99, 7 rule before, I'm kind of formalizing the work over here with what I've done in red to lead us to where we're headed on this next part. So let's look at this one, question D. Again, it's the same question stem, but now I say, what proportion of oranges are less than 8.7 ounces? And I always think it's great to start with a picture. So here's my picture. This is 8. Here's 8.7. This is 1.5. And I'm trying to find the area below 8.7. So I'm looking for this region in here. Now this is a little concerning to me because 8.7 is not a nice, neat 1.5 away from the mean. So let's see how we'd standardize it. I want to know the probability I get a number less than 8.7 when I weigh this orange. And so I need to standardize it so that z is less than 8.7 minus 8 over 1.5. And so when I solve that, that's the probability z is less than 0.467, we'll call it. Here it is over here. So we'll round that to 0.467 or 0.46 repeating, either way. Now the problem is that doesn't line up nicely with the 68, 95, 99, 7 rule. And I notice that my curve is not consistent in the slope. So I can't really estimate very accurately between that without getting a more precise method. So I'm going to take a brief aside and go over here and tell you this equation, as you might have suspected, is a function. Of course, it passes the vertical line test. And the formula for this equation or this function is either f of x or y equals 1 over sigma the square root of 2 pi e to the negative 1/2 times x minus mu over sigma squared. Now, the reason that formula makes me kind of chuckle is that it's awful. It's just brutal. It's got a sigma and a mu on there. But we don't stay there. We've also got a pi because we needed another Greek letter, of course. It's got e. I don't really even understand e, but there it is in the middle of the formula. It's got a negative exponent and a square of the negative exponent, and it's all wrapped into one just awful formula. But thankfully, we don't have to understand how that formula was derived to be able to use its results. Now, you may not have taken calculus yet, and that's fine because we don't have to know that either. But for those of you guys that have, what we really want to do is integrate this function between some certain bounds. Maybe those bounds are indefinite on one side, like a negative infinity and say a negative 0.3, or maybe they're between zero point 0.3 and 0, and we're looking for this area. But that's essentially what calculus is it finds areas underneath curves, even really awful formulas for curves. Now, some guy who was probably much smarter than all of us did this a lot and came up with an entire table that we can use here. This is the table of standard normal probabilities, and it's got just a bunch of numbers on it. So let's see what we can tell from this. First of all, you notice at the top of this particular table, there's a normal curve with the left side shaded. Okay, this will end up being important because as you use other books or other resources, sometimes they have the right side shaded, sometimes they have some middle section shaded, and it's important to see what's shaded so you'll know how the chart works. Now, as I continue to look, I see, for example, on the left side, I've got this column of Z's, and they're all negative. But over here, I have a column of Z's, and they're all positive. And then in the middle, I have a whole bunch of numbers with some hundredths up here at the top. So I want to show you how this table would work in the context of this navel orange problem. So the z-score that we got is 0.467. Now, as it turns out, this chart only goes to hundredths. So I'm going to change my 0.467 to 0.47, and I'm going to scroll over here. Actually going to take me a little picture of this. And let's look at it over here. All right, here's my table. And you'll remember my Z was 0.46 repeating, or 0.467, and we're just going to round it to 0.47. Okay, so that means the lead number here is a 0. So I'm going to look on this row, 0.4, and I'm going to go over here until I get to the 7. So it's where those two things intersect, and I got 0.6808. Now, what that tells me is the area to the left, just like this graph is shaded, the area to the left of 0.467 is 0.6808. Or in other words, this distance right here is 0.6808, or 68% of my oranges will weigh less than 8.7 ounces. Okay, that's probably still a little confusing to you. Let's go to the next one. What proportion of oranges weigh more than 11.5 ounces? Okay, start with a picture. Always start with a picture. Here it is. The middle of this is 8. The standard deviation is 1.5. This is 11.5. And I want this area more than that. So next, what do? I standardize it. I want to know the probability X is bigger than 11.5. So I'm going to standardize that. Z is bigger than 11.5 minus 8 over 1.5. My mean and my standard deviation. Now, I'm going to grab the calculator here. We're going to go 11.5 minus 8 divided by 1.5. So this is 2.3 repeating. I went ahead and put it as a hundredths in anticipation of my graph. So I'm going to cut and paste one just like I did a moment ago. Now it's 2.33. So off of my table. right, here's my table, and it's 2.3. So I'm going to go to where the 2.3 collides with 0.03, and I get 0.9901. 0.9901. Now, recall, of course, that I've got the top, I'm looking for the top half, but this graph tells me the left side. So what that means is 99.01 is this area. So to get the area to the right, it's 1 minus 0.9901 or 0.0099. Now, I understand this seems a little bit strange and foreign at the moment. You may need to slow this back down or come back and watch it later. But after you do this a few times, it'll be second nature to you. Let's look at one more. What proportion of oranges are between 6.2 and 7? Start with a graph. Translate this into math, standardize it, and use the chart. 8, 6.2, 7, 1.5, and that's the area I'm looking for. In math, that looks like this. So now I want to standardize them. Each number minus the mean divided by the standard deviation. Grab your calculator and work these out. So this is 6.2 minus 8 divided by 1.5. And again, it's negative because this number is less than the mean. And then this side is going to be also negative, right? Because it's less than the mean. Whoop. 7 minus 8 divided by 1.5, negative 0.67. All right, now this is going to be a little bit different because I've got a between here. So when I look these two numbers up, they're going to tell me the area to the left. So when I look up 1.2, it's going to give me this area. When I look up negative 0.67, it's going to give me this area. And if I subtract them, in this case blue minus green, I'll be left with what's in the middle. And actually this little blue should be slid down here, right? All right, so let's see if we can make this work. All right, looking up first, this blue one, negative 0.67. So I'm going to look at my chart. Negative, now that's over here on this side. So I got negative 0.67. It's right here. 2514. 2514. That's 2514. That's the blue number. That's the area to the left of that. Now I want to find the green number, negative 1.2. So negative 1.2. Now that's negative 1.20. So it's this number right here, 0.1151. 0.1151. That difference or that distance between those two numbers is my area. 0.1363 is the area between them. All right, let's do one last problem. Find the value of x below which you will find the lightest 80% of oranges. Uh-oh. All right, so let me draw a picture, see if I can make sense of it. I already know this. This is 8. This is 1.5. Okay, the lightest 80% of oranges. So somewhere I've got a bar, and the area to the left of that bar needs to be 80%. So the question is, where does that bar go? Does it go here? Does it go here? Does it go over here? Well, first of all, I know it's got to go to the right of this number, because over here this would be less than half. So it's somewhere in here. I'm not exactly sure where, but I do know that this, I know that this, one more try, this area is 80%. This shaded blue region has to be 80%. The lightest 80% are over there. Now I'm on the inside of my graph right here. So I'm going to look on the inside of this table for the number that's closest to 0.80. And as I look at this, I see point, this number here is really close to that, which means the z-score that goes with this is 0.84. 0.84. So in terms of z's, this number is 0.84. But my question is, what is that number? Well, z equals x minus mu over sigma. My z, we just said, was 0.84. The x is what I don't know. Mu is 8. Sigma is 1.5. So I've got 0.84 times 1.5 plus 8, 9.26, which means 80% of oranges, now that is hardly legible, 80% of oranges weigh less than 9.26 ounces. Now, like I mentioned a second ago, this is a pretty fast and furious introduction to the table of standard normal distributions. It may take a second watching, or you go back and look at this problem, try to work it on your own, see if I did it right. I hope I did. And that should give you a good idea or a good foundation for how this table actually works.